Good morning everyone, my name is Martina TOSCANI and I am a third year PhD student at Università degli Studi di Milano. With this brief talk, I would like to introduce you to my research topics with a particular focus on what I did inside the Dustbusters project. In this video, you may see a Tidal Disruption Event, TDE. A TDE takes place when the self-gravity of a star orbiting around a black hole is overwhelmed by the black hole tides, and thus the star is torn apart. After the disruption, around half of the stellar debris escapes on different parabolic orbit, while the other half circularizes around the black hole and forms an accretion disk. TDEs will be promising sources of information in the upcoming years inside the field of multimessenger astronomy. Indeed, we know that they are very luminous electromagnetic sources characterized by flare, which are often super Eddington. So far, around 50 events of this type have been observed, with a light curve that at late times is proportional to time to minus 5/3. Moreover, TDEs also emit gravitational waves, and this is why they will be so important in the astrophysical research in the upcoming years. Talking about single tidal disruption events, we have that gravitational waves are emitted both during the disruption of the star and then during the circularization of the debris. During the disruption, we have the production of a gravitational wave burst in the low frequency regime. This is the same regime where the future interferometers such as LISA, Tianqin and the SIGO will work. Unfortunately, this signal does not seem to be very strong, and this is why I'm taking part into a paper where we are deriving the precise rate of detection of tidal disruption event through gravitational waves per year by future interferometers. As for the signal emitted when the disk is formed, this is in general lower than the signal produced during the disruption. You can find much detail about the signal at the later stages of TDEs in the paper TOSCANI et al. 2019. Since the gravitational signal from single tidal disruption event does not seem to be very strong, it can be very interesting to understand which is the gravitational wave background that we expect from the entire cosmic population of tidal disruption events through the universe. This work has been done in TOSCANI et al. 2020. Where they found that this background is proportional to the frequency of the signal to minus 1/2. Moreover, they discovered that if we consider white dwarfs disrupted by intermediate mass black holes, this signal will be a promising source for future planned interferometers such as the SIGO and BBO. Now, let's focus on what I'm doing with my research inside the Dustbusters project. Within this project, I work with Phantom, the smoothed particle hydrodynamics and magneto-hydrodynamics code for three-dimensional simulation of astrophysical events. In particular, I work with GR Phantom, the latest version of the code presented in Liptai and Price 2019. This is a full general relativistic version of the code, which is, for instance, able to capture relativistic shocks and to work in Kerr geometry. Inside this code, I have implemented a tool for the calculation of the gravitational wave emission from the various astrophysical systems simulated with Phantom. We calculate this emission through the velocity and acceleration of the SPH particle, which is the most natural way to implement this feature in an SPH code. We have performed many tests to verify that the algorithm was working properly, and now we are about to publish all our results in an upcoming paper. Moreover, We are using this tool to build a huge online library of tidal disruption event gravitational waveform that anyone in the scientific community will be able to use completely free. So please stay tuned and don't miss any updates. And with this final slide, I thank you for your attention.